Hi boys and girls, welcome to my YouTube channel. So today we are going to discuss what we call Thevenin's theorem. In the previous class, we managed to solve many problems related to the superposition theorem. We used the superposition theorem together with mesh analysis and node analysis to solve electrical circuits. Okay, so today we are going to discuss about Thevenin's theorem. See, you are supposed to know Thevenin's theorem first. Okay, if I ask you to state Thevenin's theorem, you should be able to state Thevenin's theorem. Okay, what is the meaning? You should know what this Thevenin's theorem means. Okay, so Thevenin's theorem states that a linear circuit with the two terminals can be replaced with an equivalent circuit consisting of a voltage source in series with a resistance. You have a linear circuit with the two terminals. This linear circuit with the two terminals can be replaced with an equivalent circuit consisting of a voltage source in series with a resistance. Okay, let's say you have an active RLC circuit. Okay, what is an active RLC circuit? See, this active RLC circuit, it consists of resistors, inductors, and capacitors. Also, there is power supply. Okay, so this active RLC circuit is nothing but this. This is the network. Remember, I told you in the previous class, all circuits are networks. Okay, all circuits are networks. Okay, but not all networks are what? Are circuits. This statement is important. You may be confused why is saying this is an active RLC circuit, but now he's saying this is a network. See, all circuits are what? Are networks. But not all networks are what? Are circuits. So this is an active RLC circuit. If it is an active RLC circuit, it means there are resistors, inductors, and what? And capacitors. There also power supply is also there. Okay, so what will happen here? This active RLC circuit has two terminals. Okay, suppose this is the current from this what? Network. This is I. This is the potential difference across the two what? Across the two terminals. Okay, so Thevenin's theorem is saying this circuit now, this active RLC circuit, this network now, you can remove this network, okay, and you can replace it. You can replace this with a voltage source and a resistor in series. See, this voltage source is in series with this resistor. Okay, this is A, this is A, this is B, this is B. These are the terminals, positive, negative. Okay, so you can replace this network with a voltage source and a resistor in series. Okay, this voltage source is called the Thevenin's voltage. It is called the Thevenin's voltage. We are going to represent it with capital letter V subscript TH. And this RTH is called Thevenin's resistance. Is called Thevenin's resistance. Okay, so when you are doing, you are solving a circuit now using Thevenin's theorem. See, this part will have many resistors. In some cases, inductors and capacitors are going to place. Let's say we have a circuit with many resistors, some are in parallel and some are in what? Are in series. Okay, and sources are there. Maybe current source and voltage source. Many current source and voltage source are also there in this what? In this network. So you are supposed to reduce the whole network in such a way that you can have only one voltage source, which is the Thevenin's voltage, and only one resistance, which is the Thevenin's resistance. Okay, and present it like this. Okay, so this is called the Thevenin's equivalent circuit. The Thevenin's equivalent circuit. This is called the Thevenin's equivalent circuit. Okay, here we are. So in order for you to reduce all these things, see, we have independent voltage sources, I said, we have independent current sources, they are there in the network. How are we going to calculate the Thevenin's resistance? So if you want to calculate the Thevenin's resistance, okay, you are supposed to short circuit the independent voltage sources, and you are supposed to open circuit the current sources. You do this at one time. Okay, you replace all the independent voltage sources with a straight line apart, like short circuiting. Then you open circuit all the current sources. Okay, then you will be able to calculate the Thevenin's resistance. Okay, let's say you have the Thevenin's resistance. Now you are supposed to calculate the Thevenin's voltage. In order for you to calculate the Thevenin's voltage, I will demonstrate with the help of an example. This theorem is not applicable to unilateral and non-linear networks. Okay, I told you that we have unilateral networks and bilateral networks. I explained all these things in the previous classes. If you don't know what is a unilateral network, go back and check. If you don't know what is a non-linear network, go back and check what is a non-linear network. Okay, have a good day. I will see you in the next class. Thank you.